Hi everyone, hope all of you are doing well. In this video, we are going to talk about hypothesis test for a population mean. So in general, all hypothesis tests follows a rule. We need to make a claim or assumption. We need to collect some data. If the data is in contradiction with the claim or assumption, then we conclude that the claim made must be wrong. So for example, look at here, there are examples of some claim or assumption. So a manager can claim that the box of cereal has a mean fill of 100 ounces. It's a quality control department can make this claim, okay? Or it's another claim or assumption. Average waiting time in a clinic is less than 15 minutes. We can test, we can check if it's correct or no by hypothesis test, okay? So look at here you can find the steps for hypothesis testing. So we have a claim or assumption. For that claim or assumption, I need to formulate null and alternative hypotheses. In step 2, I need to select a level of significance, and it's always given in the question. And then we need a sample in step 3. Then, okay, we need to identify the region of rejection. And based on the sample, we need to calculate the test statistic. And then in the last step, we need to decide about rejecting or not rejecting the null hypothesis. Okay, so look at here. Let's talk about step 1, how to formulate hypothesis for population mean. Okay, we can follow the same steps for hypothesis testing for proportion, for example. So look at here. While when you are going to formulate hypothesis for the mean, you need to form two hypotheses, null hypothesis and alternative one. The null hypothesis or H0, we made that based on the information in the claim, and also we make the alternative one based on the information we have in the claim or assumption. I'm going to show you I'm going to show you how to make them in some examples. So look at here, while making H0 and H alternative, you need to cover all the possible values for the population mean. Okay, so you need to make them in a way that they are complement to each other. So, and it's very important. We always need to have equal sign in the null hypothesis in H0. So for example, let me show you how to formulate H0 and H alternative, null hypothesis and alternative one for this example. Example says the bag of flour has a mean fill of 100 ounces. Okay, so I'm testing if the mean is 100. Okay, because look at here, because I have equal sign and we need to have the equal sign in the null hypothesis. In the null hypothesis, H0 or null hypothesis would be H0 would be mu equals 100. So, and because I told you H0 and H1 null hypothesis and alternative one always are complement. Okay, they must cover all the possible values for the mu, for the population mean. And because H0 says mu is equal to 100, in H1 we need to have mu is not equal to 100. Okay, then I have covered all the possible values of mu. Mu is 100 or mu is not 100. So look at it, it's very important. In H0 and H1, we need to work with population parameter, not sample statistic. We don't work X bar, we don't work with S. We always work with something related to population, mu, sigma, okay? And but here we work on mean. So we have written mu, population mean. So when in H0 and H1, we have equal sign and not equal sign, we call that a two-tailed test. I'm going to explain why we call that a two-tailed test later. So let me show you how to formulate hypothesis H0 and H1 for this question. Question says average wait for this example says average waiting time in a clinic is more than 15 minutes. We are going to make a hypothesis testing for this claim or assumption. Average waiting time mean is more than 15. Look at here. Here I don't have any equality, so it cannot be H0. So that's H alternative. Already I have made H alternative. Okay. And as a result, H0 null hypothesis would be, what is the complement of mu is more than 15? So mu is less than or equal to 15 then. Look at here, I have formulated H0 and H1 for this assumption and claim. Okay, so it's a step one. Here, I have a one-tail test. When we don't have equal sign or not equal sign, we have more than or less than, we call that a one-tail test. It's one-tail test, and here tail is on the up. Look at here, we have a situation like this one. It's one tail and tail is on the top. I'm going to explain about that later in the next slide, okay? So let's formulate H0 and H1 for this example. An environment department has stated that average annual rainfall in a particular country is at least 25 minutes. So the average is at least means more than or equal to 25. It can be 25, 26, 27 and more. So here, because I have equal sign, that would be H0. Okay, so as a result, alternative one would be mu is less than 25. Look at here, again here, because I don't have equal sign and not equal sign, we have more than or less than, it's a one-tail test. Okay, we call that a one-tail test, and it's lower tail test. An easy way to identify if we have lower tail test or upper tail test is to look at H1, H alternative. If mu is less than something, if the population parameter is less than a number, we have a lower tail test. If the population parameter mu is more than something in H alternative, we look at H alternative to find, it's an easy way to find if the test is upper tail test or lower tail test. If in H alternative mu is more than a number, we have upper tail test. Okay, in step 2, after formulating H0 and H1, I need to select a level of significance. The level of significance is the probability of rejecting the null hypothesis while it's true. Look at here. The last step in hypothesis testing is to decide about rejecting or not rejecting H0, okay, null hypothesis. So the level of significance is the probability of rejecting the null hypothesis while it's true. In this case, we have made an error. Okay, so it's called level of significance, alpha. Alpha is probability of rejecting H0 while it's correct. Okay, if based on a sample we reject H0 while it's correct, it means we have made a type 1 error that has a chance or probability of alpha. Okay, so alpha is a probability, it's an area. So there are accepted values for alpha, 5%, 1%, and 0.1. So after selecting a level of significance, I need a sample. Okay, I need a sample and I need a sample mean. When I'm doing hypothesis testing for the population mean, I need a sample mean. If the sample mean is inconsistent with the null hypothesis, it means if the sample mean x bar is very small or very low, very small or low or very large. Okay, we reject H0. Okay, so look at here. Let me talk about this example. Look at here. It's a hypothesis. H0 and H1 we made in some for a claim. For example, in some slide before. Okay, so Look at here, I told you we have a two-tailed test, but why we have a two-tailed test? So look at here. Look at here. We need to select a sample in step 3, and we are going to work with sample mean. Okay, so the distribution of x bar or sample mean is a normal distribution. Okay, it's bell-shaped. Okay, so if we reject H0, it means x bar is very large or x bar is very small. Okay, so it means x bar, when x bar is very large, it means x bar is on the right tail. But what happens if x bar is very small or low? Then x bar is on the left tail. Look at here, in this shape I have two tails. Right tail, a tail on the right side and a tail on the left side. If x bar is very large, okay, and it's inconsistent with the null hypothesis, I'm gonna reject H0. Okay, so when x bar is too large, x bar is on the right tail. If x bar is too large, it's very large, x bar is on the right side tail. So, and then I'm gonna reject H0. Okay, if we reject H0 while it's correct, it means x bar falls in the tails. Okay, in this case, the chance that x bar falls in the tail is alpha. And because I have two tail, one tail on the right side, another tail on the left side, okay, the area of each tail would be alpha divided by 2. So look at here. In the last slide, we talked about alpha, level of significance. This alpha is the area of the rejection region, okay, or probability of rejecting H0 while it's correct. Okay, so if I reject H0 while it's correct, I have made a type 1 error. I have made a type 1 error, okay, that has a chance or probability of alpha. Okay, so it means x bar falls in the tails when we reject H0. X bar falls in the tail, right tail or left tail. Okay, so because x bar is too large or too small. Okay, so, and because there are two tails and alpha is the probability of rejecting region, and I have two tails, each tail would be alpha divided by 2. Because I have two rejection region, one on the right side, another on the left side. And in total, the probability of the rejection region, tails are rejection region, okay? So, and because the probability of the area of the rejection region is alpha, and I have two tails, two rejection region, each rejection region would be alpha divided by 2. So because of that, we call that a two-tail test. Okay, so to identify the rejection region clearly, I need this cutoff point and this cutoff point. If I calculate this cutoff point on the right side, then the cutoff point on the left side would be exactly the negative one of the number on the right side. Just I multiply the number on the right side by negative, we get this cutoff point on the left side. Okay, to find this cutoff point, just I need Excel. Okay, in Excel, just I need to type norm S inverse. Look at here, I'm working with standard normal distribution, but inverse one. Okay, and look at here, I have the probability or area on the right side of this cutoff point. Okay, and I'm looking for the cutoff point. but this function just accepts the area on the left side. Okay, so when the area on the right side of cutoff point is alpha divided by 2, the area on the left side of this cutoff point would be 1 minus alpha divided by 2. Okay, and it's inverse V. Just by using Excel, you can find this cutoff point. I'm going to show you on a real example to how to find that in Excel. And then this cutoff point would be minus negative norm period S period inverse 1 minus alpha 2, or very simple. In another, you can find that by norm period S period inverse alpha divided by 2, because we already have the area on the left side. So it's the reason we call this test, when we have equal sign and not equal, we call that a two-tailed test, because we have two rejection region. So, but sometime after formulating H0 and H1, we have less than or more than for population mean. In this case, we have a one-tailed test. Okay, why? Because in this case, X bar is very large. Okay, if X bar is inconsistently large with the null hypothesis, we reject H0. Okay, so look at here, when X bar is very large, X bar falls on the tail on the right side. Okay, I have a one tail test. We have just one tail because X bar here is so large, very large, and it's inconsistent with the null hypothesis. So if X bar falls on the right side, okay, in this tail, we have a one tail test. But you can look at the alternative one, H1, to identify if you have a one tail test or two tail test. Okay, so the rejection region is on the right side. But what about this one? Look at here, H0 is mu is more than or equal to 100, but H alternative, H1 or HA is mu is less than 100. An easy way, because mu is in H alternative, mu is less than 100. Okay, so we have a lower tail test. Tail is on the left side. Okay, but we have another rationale for that. In this case, we reject H0 if the sample mean is very small. Okay, and it is not consistent with the null hypothesis, because null hypothesis says mu is more than 100, mu is large. Okay, but if the sample mean is very small, okay, it means the sample mean X bar is on the left side here in this tail on the left side. Okay, so, and if the sample mean is very small, we reject H0. So the rejection region in this case would be on the left side, and alpha would be the area of the tail on the left side. Look at here, in this question, alpha level of significance would be the probability or area of the right tail. Tail is on the right side, and alpha is the area of this tail. Okay, when tail is on the left side, alpha level of significance is on the left side. It's the area on the left tail, lower tail test. And this cutoff point, look at here, I can find this cutoff point. We need this cutoff point. This cutoff point can be, you can find that by norm period S period inverse alpha. This cutoff point, we need them because we need to identify clearly the tail. This cutoff point in Excel can be found by norm period S period inverse, and this function just accepts the area on the left side of the cutoff point. The area on the left side of cutoff point is alpha. Okay, what about this one? I need this cutoff point in solving the question. This cutoff point can be found by norm in Excel, norm S standard inverse. But this function just accepts the area on the left side. When area on the right side is alpha, the area on the left side would be 1 minus alpha because total area on the curve is 1. Okay, they are cutoff point. We need to clearly identify the tail, the rejection region. We need to find the cutoff point. Okay, so after identifying the rejection region, we need to calculate the test statistic. If you are doing a hypothesis testing for the mean, for the population mean and sigma, population standard deviation is known, it's given in the question, you need to calculate Z statistic by this formula. Z is x bar minus mu over sigma over square root of n. N is sample size. X bar sample mean, mu population mean, sigma population standard deviation. Okay, then after finding Z, if Z falls in the rejection region, if Z falls in the tails, we reject the null hypothesis. Otherwise, we don't reject the null hypothesis. It's the last step. So let's solve an example. Look at it in this question. Sigma is known. Sigma is given in the question. Question says a study conducted by a train transportation authority with a random sample of 300 passengers shows that a customer had to wait on average 10.3 minutes with a standard deviation of 6.2 minutes. Look at this, sigma standard deviation is known, 6.2, to buy their ticket. It is suspected that the actual average waiting time is not 3.3 minutes. Look at here. We are going to make a hypothesis testing for this claim. What is the claim? They are claiming that the average waiting time, mu, is not equal to 10.3. Okay? So, look at here. To test this claim, I need to formulate H0 and H alternative. Because in the claim, I have mu is not equal to 10.3. It cannot be H0. So that would be H alternative, HA or H1. Okay? So as a result, H0 would be mu is equal to 10.3. Okay? Step 1, we formulated H0 and H1. So in step 2, I need to identify level of significance. Alpha is given in the question. Alpha is 5%, 0.05. Okay, look at here. A random sample of 184 customers. Out of that, 300 customers showed a mean of 9.3. Look at here, they have selected a sample of 184. Sample size, n. N is 184. And the sample size and the sample mean is how much? Sample mean x bar. X bar is 9.3. A random sample of 184 customers showed a mean of 9.3. Its sample mean x bar. X bar is 9.3. Shall we reject the hypothesis that the population mean is 10.3? Okay, so I'm going to do a hypothesis testing for this claim. Okay, we formulated H0 and H1. It's step 1. Level of significance is 0.05. I need to identify the rejection region. Okay, so X bar is bell-shaped. Okay, and look at here. Here I have a two-tail test because mu is in the mu in H0 I have mu equals, and in H alternative we have mu is not equal. We have a two-tail test. Okay, we have a tail on the right side, a tail on the left side. As I explained before, the area of both tails is alpha, and in total the area of the right side tail and plus the area on the area of the right side tail plus the area of the left side tail together is 0.05. So each tail would be in this case alpha divided by 2. Each tail is alpha divided by 2, or 0.05 divided by 2. It's the area of each tail. Each rejection region. We have two rejection regions, one on the right side and one on the left side. So on the left side, again, I have a tail that its area is 0.05 divided by 2. Okay? So I need the cutoff point. I need to identify the rejection region clearly. Okay? I need this cutoff point and this cutoff point. So we know that this cutoff point can be got by norm period S period inverse 1 minus alpha divided by 2. Alpha is 0.05. Alpha divided by 2 would be 0.05 divided by 2. Okay, so let's go to Excel to find the cutoff point. Okay, I need this cutoff point and this cutoff point. Look at here. It's the Excel file for the same question. X bar is 9.3, mu is 10.3. In H alternative, mu is 10.3. Okay, so I need the cutoff point. To find the cutoff point, I need this function, norm period S inverse. Okay, I'm looking for the cutoff point on the right side. So, and the cutoff point on the right side, the area on the right side of the cutoff point is alpha divided by 2. Okay, alpha divided by 2, alpha is 0.05, then divided by 2. Sorry, here I need to 1 minus alpha divided by 2, because alpha divided by 2 is the area on the left side. But I'm looking for the cutoff point on the right side. So the area on the right side of the cutoff point on the right side is alpha divided by 2, 0.05 divided by 2. So the area on the left side would be 1 minus alpha divided by 2. So look at here, I get 1.96. So this cutoff point, this point is 1.96. So as a result, this cutoff point would be minus 1.96 because the shape is completely symmetric. Okay, 1.96 minus 1 would be on the left side. Minus 1.96, it's on the left side. We have two cutoff. So now we identify the rejection region. The next step is to find the Z value of X bar. We need to find the Z value of X bar by this formula. X bar minus mu over sigma over a square root of n. Okay, I need to find this Z value. If the Z value falls in the tails, we reject H0. Otherwise, we don't reject H0. If Z value falls in the middle, okay, if Z value falls between minus 1.96 and 1.96, we don't reject H0. But if Z value falls in the tails, we reject H0. We reject null hypothesis. Let's go to Excel to find Z. X bar minus mu over sigma over square root of n. Okay, look at here. Look at here in the Z. Look at the Z formula. In the Z formula, first I need to find sigma over square root of n. So let's find that. Let's find sigma over square root of n. Sigma is how much? Sigma in the question is standard deviation, 6.2. So sigma is 6.2. Let's find this one. So 6.2 divided by a square root of n. N was how much? So yeah, I forgot to enter n one more again. We have a sample of 184. 184. So now let's find sigma over square root of n. Why? Because in the z formula I need that. So now sigma divided by square root of 184. So we get 0.45700. Now by using z equals, look at the formula for z. By using this formula, z is x bar minus mu over sigma over square root of n. We already got sigma. We already calculated sigma over square root of n. Just now I need to calculate z. Now to find z, x bar, I need a bracket here. X bar minus mu 10.3 divided by sigma over square root of n. We already have the number here, enter. Okay, we get minus 2.18. Okay, it's the z value. So z value is minus 2 point approximately 1878. 1878. Look at the z value. Z value is minus 2.18. It's in the tail, in the left tail, because minus 2.18 is on the left side of minus 1.96. The z value falls, for example, z value is here. Z value falls in the left tail, in the rejection region. When the z value falls in the rejection region, we reject H0. Okay, so we conclude here that the average waiting time is not 10.3 minutes.